This video is the solution to number 57 in chapter 28. The problem gives us this sphere with radius r, charge q, and charge density rho as a function of r equal to c, which is some constant, over r squared. First, we're asked to determine c in terms of q and r. Then we'll use Gauss's law to find the electric field inside the sphere. And then we'll look at the expression that we found and ask if it has the expected value at the surface of the sphere or at r is equal to r. So for part A, we'll start with the integral of q enclosed is equal to integral of rho times dv. Now we can plug in c over r squared as rho. And for dv, we can plug in r squared dr sine phi d phi d theta. Now from our knowledge about spheres, we know that the r squared dr sine phi d theta part of the integral can be simplified to r squared pi 4 dr. So plugging that into our integral, we get QE equals the integral of 0 to r of c over r squared times 4 pi r squared dr. Simplifying further, we can plug in r and find that our integral equals q equals 4 pi cr. And now solving for c, we get q over 4 pi r. And that is our solution to A. Moving to solution B, we're asked to use Gauss's law to find the electric field inside the sphere. So we have some charge dq equal to the integral of rho dv. Now substituting in using our knowledge about rho from the previous problem, we can plug in 4 pi c dr. And again, from solving for c above, we can plug in for c in the integral. And solving throughout, we get dq equals the integral of q over r dr. And since q and r are both constants, we can pull them out of the integral. And it's a very simple integral, it turns out. So we solve it from 0 to r, and we get that the charge, or the dq, equals q times little r over big R. Continuing on plugging it into Gauss's law, we know that the surface of a sphere is 4 pi r squared, and that pretty much solves it for the left side. And then on the right, we can plug in for q enclosed what we just found up here. So plugging that all into Gauss's law, we get this equation, where the electric field will equal the charge of the sphere times k, our constant, divided by r times big R. Now for part C, we're asked, does the expression have the expected value at the surface of the sphere when r is equal to big R? So we'll plug in big R for little r in the equation we found in part B, and as we plug that in, we can see that yes, we're going to have the expected result because E is equal to k, or q times k over r squared.